Good morning, everybody. Today we're going to be talking about prime factorization and creating factor trees. So let's talk a little bit about what that means. Well, to factor something means to break it down into numbers that multiply to another number. So you may have heard of finding the factors of a number. Like if you want to find the factors of 10, you find all the numbers that go into 10 that you could multiply by something to get 10. So we're taking a bigger number and we're breaking it down into smaller pieces. Well, this isn't just any kind of factorization either. This is prime factorization. Prime factorization means we're going to break it down into just prime numbers. So here's the first thing that we're learning today. And it's a pretty cool statement, but here's the idea. Every single number that's not a prime number, every single number whole number can be broken down into a bunch of prime numbers multiplied together. Okay? And it works with every number that's not already a prime number. Okay? And you'll see as we go through each of these numbers what primes they break down into. And if you want to think of any number you want on your own, as long as it's a positive whole number and not already prime, you can find prime numbers that multiply to give you that number. And when you find what prime numbers do that, it's called prime factorization. Now you might also notice I got some Legos up here at the top. Now here's why I have Legos. I want you to start thinking about prime numbers as the building blocks of other numbers. So if you've ever used Legos before, you know you can build bigger things out of these little pieces, but the pieces themselves can't be broken up any further, or at least not without a hammer, and you probably shouldn't do that. But each one of our prime numbers is going to be a Lego, and we're going to be able to build other numbers using these Legos. And you'll see what I mean by that. So let's start with 36. So if I'm trying to find the factors of 36, I want to start by finding two numbers that multiply to 36. I have a couple of different options here. It doesn't matter which one I choose. I'll end up at the same place no matter what. So I'm going to start with 12 and 3. Okay. So 12 and 3 are two numbers that multiply to 36. Now, if either one of these numbers is prime, I'm going to circle it and be done with that part of the tree. If it's not prime, I'm going to keep going. So in this case, 3 is a prime number, so I'm going to circle it. Okay, so you got instruction here, circle prime numbers only. So I'm not going to circle the 12 because that can be broken down further. So now I want to think of two numbers that multiply to 12. Again, I have a couple options. I'm going to go with 3 times 4. Okay, again, 3 is a prime number, so I'm going to circle it. 4 is not a prime number, so I can keep going. So if I look at what makes 4, well, that's 2 times 2. And wouldn't you know it, 2 is a prime number. Okay, so here we have 4 numbers that if we multiply them all together, we get 36. Let's make sure that's true. 3 times 2 is 6, times 2 is 12, times 3 is 36. Okay, so when I talk about the prime factorization of 36, I can see that 36 is basically built out of 2 2's. Oh. It's built out of 2 2's and 2 3's. So here's a visual representation of what 36 looks like. It's made up of 2 factors of 2 and 2 factors of 3. Multiply all these together, you get 36. So each number is going to have its own unique set of Legos that make up that number. Okay. So once we have it broken down into its prime factors, we're going to write it as a product of primes, and we're going to use something called exponential form. So here's what that looks like. So we've talked about exponents before. An exponent happens anytime you're multiplying a number by itself. And the exponent tells you how many times you're multiplying that number by itself. So we're going to express this by taking each one of our Legos, each one of our prime factors. This has 2's and 3's. And we're going to write that. And the power that we're going to use is going to be however many times we have that Lego. So having two 2's is the same as 2 times 2. We're going to write that as 2 to the second power. Okay, I also have two 3's, so I can write that as 3 to the second power. Okay, because again, that means we're multiplying these together. So multiplying two 2's is 2 to the second. Multiplying two 3's is 3 to the second. And then we're multiplying all of them together. Okay, so when we put it in exponential form, we want to make sure we're using the exponents to show you how many times each factor shows up. If something only shows up one time, we don't need to have an exponent for that. And we'll see examples of that in a little bit. Okay, so let's get the definition of prime factorization down. Prime factorization is a number expressed as a product of primes. Product means you're multiplying things. So we're multiplying prime numbers. So that's what product of primes means. Using factor trees, so that's how we find what the primes are. Then express the result in exponential form. So that's where we're using exponents to show repeated factors, how many times they come up. Okay? So pause video, make sure you have that definition down, and then we'll do a couple more examples. All right, next example is 80. So I want to know what Legos, what prime factors are going to make up the number 80. So I'm going to start with 80, and I'm going to break it down. So I just need to find two numbers that multiply to 80, and it doesn't matter what I use. This is a good place where we can use some of the divisibility rules we talked about yesterday also. If you're not sure what goes into 80, try testing some of the rules. Okay, I know it's an even number, so it's divisible by 2. If I want to check to see if it's divisible by 3, I would do 8 plus 0, which gives me 8, which is not divisible by 3. So I can't divide it by 3. It is divisible by 4 or 5 because it ends with 0, or 10. Okay, so all of those are options. I'm going to divide by 10. So I'm going to write 80 as 8 times 10. Okay, if I do that, neither one of these is prime. They can both be broken down further. So I'm going to do that. 8, I'm going to say is 4 times 2. And here I got my first prime number. It's 2. Okay, 4 can keep going. 4 breaks down into 2 and 2. And again, I'm looking for numbers that multiply to these numbers, okay, not add. So 4 times 2 is 8. 8 times 10 is 80. Okay, 80 the 10 I still need to break down. 10 I can say is 2 times 5. And both of those are prime numbers, so I can circle them. So when everything is said and done, I have 1, 2, 3, 4 2's and 1 5. Okay, so if I want to see what this looks like, I got 1, 2, 3, 4 2's and 1 5. And this is the unique factorization, the unique set of Legos that gives us 80. Okay. If I want to write this in exponential form, I see I have 4 2's. So I'm going to write that as 2 to the 4th power. And then we're multiplying that by 1 5. So I'm going to write 5. I only have 1 5, so I could write 5 to the 1st, but I don't need to. Right? I only need exponents if I have more than 1. So 2 to the 4th times 5 is my prime factorization. If you want to check that and make sure, you can find 2 to the 4th, which is 16, times 5 gives you 80. Okay. All right, let's try 135. So again, here's one. You might not have things jump out at you for what you can divide this by. I do see that this ends with a 5, and the fact that it ends with a 5 tells me that it's divisible by 5. So I'm going to start out that way. So 135, if you divide that by 5, again, I might not know what that is off the top of my head, so I'm going to pull it over here, do my long division. Okay, 5 doesn't go into 1, it goes into 13 twice. 2 times 5 is 10. Subtract 13 minus 10, I get 3. Bring down to 5. 5 goes into 35 7 times exactly. Nothing left over. And I knew there was going to be nothing left over because I know 5 goes into 135 evenly. Okay. So 135 is 5 times 27. 5 is a prime number, 27 is not. Okay. If I use my 3's test, I can do 2 plus 7 gives me 9. That tells me this is divisible by both 3 and 9. Okay. So let's divide it by 3. Okay, so 27 is 3 times 9. 3 is prime number. 9 breaks down into another 3 times 3. Okay, so when everything is said and done, I have 1, 2, 3 threes and a 5. Okay, so I would write that as 3 to the third power, because there's 3 of them, times 5. And there's only one 5, so I don't need an exponent there. 3 to the third times 5. Okay, if you want to know what that looked like with Legos, well, here's how we're doing our Lego representation of 135. Right, it's made out of 3 threes and 1 5. All right, let's try 150. So 150, there's a couple different ways we could break this one up too. I'm going to start by breaking that into 350s. I know 3 times 50 will give me 150. Okay, 3 is a prime number. I'll circle it. 50 I can break down into 5 times 10. 5 is a prime number, so I'll circle it. And then 10 breaks down into 2 times 5. Both prime numbers. Okay, so in exponential form, I'm going to just go from the smallest number to the biggest number, just to keep it easy. So I have 1, 2. I don't need an exponent because I only have one of them. I have 1, 3. And I have 2 5s. So 5 is going to be to the second power. So 2 times 3 times 5 to the second power will give me 150, and that's the prime factorization. Okay, looking at our Legos, that means we got 1, 2, 1, 3, and 2 5s. There's 150. Okay. Now, I told you before it doesn't matter what we start with, and I'm going to prove it right now. So we're going to take 150. If you want to pause and think about another way to break this down instead of starting out with 3 times 50, go ahead and do that. I'm going to do it a different way so you can see that we end up with the same answer. Okay, so another way we could have broken this up is maybe 15 times 10. That also gives me 150. 15 breaks up into 3 and 5. And 10 breaks up into 2 times 5. So I'm in a little different order here, but order doesn't matter with multiplying, right? Okay, in both cases, I end up with 1, 2, 1, 3, and 2 5s. All right, so it gives me the same set of Legos there. All right, let's try 200. 200, a lot of ways to break this one down also. I'll just do maybe 2 times 100. Okay, so 2 times 100. 2 is prime. 100 I can say is 10 times 10. And 10 I can say is 2 times 5. Okay, so when we're all done, we've got all our prime numbers circled. I have 1, 2, 3 2s. So I'll write that as 2 to the third power. And 2 5s, so I'll write that as 5 to the second power. So 2 to the third times 5 squared gives me 200. Three 2s and 2 5s. There it is with Legos. Okay. All right, 144. Let's try this one. So 144, you might be familiar with as 12 times 12, depending on how well you know your multiplication facts. So let's start there. 12 times 12. Okay. If you didn't know that, you can try your rules. You know it's divisible by 2 because it's an even number, so you could start with 2 times something. If you added the digits, 1 plus 4 plus 4 is 9, so you could divide by 9 or by 3 to start. Okay, I'm just going to do 12 times 12, but both of those would work. 12, let's do 6 and 2 over here, just to be different, and 3 and 4 over here. Okay, 2 is prime number, 6 is not. 6 is made up of a 2 and a 3. Okay, 3 is a prime number. 4 is not. It's made up of 2 2s. Okay, so everything together we have 1, 2, 3, 4 2s. That's 2 to the 4th. And 1, 2, 3. So 3 squared. Okay, so that's the prime factorization of 144. All right, let's try a challenge one. Let's come up with a tricky number and see if we can break it down. Let's do 980. No, let's do 1,470. Yeah, that's a good one. All right, 1,470. You ready? All right, think you can do this one on your own? Pause the video, see what you get, and come back and we'll compare answers. All right, 1470. First thing I notice is it ends with a 0, which tells me I can divide it by 10. So I'll do 470 times 10. Okay, the 10 branch is pretty easy. That's 2 times 5. Good to go. For the 147, there's nothing obvious that's jumping out that I can divide by. So I'll check my rules. Is it divisible by 2? No, it's not a number. Is it divisible by 3? Well, 1 plus 4 is 5, plus 7 is 12. Okay, well 12 I can divide by 3, which tells me 147 is divisible by 3. Okay, so to find out what two numbers would multiply to 147, I'll take and divide by 3. Right? 3 doesn't go into 1, it goes into 14 4 times. That's 12, I get 2. Bring down the 7. 3 goes into 27 9 times. So that tells me 147 is 3 times 49. 3 there. 49 there. Oh, I'm sorry, I shouldn't have circled that one. That is not prime. I almost did it again. Yeah, let's try a different number. So let's try 408. Okay, so I just need to find two numbers that I can divide this by. If you're not sure where to start, just use your divisibility rules. I can see right away it's an even number, so at the very least I can divide it by 2. So let's divide it by 2. So 408 divided by 2 is 204. So 204 times 2 would give me that, and 2 is prime. Okay. Well, this is still an even number, so I can just divide by 2 again. Half of 204 is 102 times 2, and it's still even, so I can still keep using this trick, divide by 2 again, and I get 2 times 51, gives me 102. Okay. If you're not sure about any of those divisions, right, you can just go over here and do some long division. We know how to do that. Okay, there's an example. All right, so 51 is no longer even, which means I can't divide by 2's anymore. Well, let's check 3's. 5 plus 1 is 6. 6 is divisible by 3. So that tells me that 51 is divisible by 3. Okay, so I have a 3 times something. Okay, come over here to find out what. 3 goes into 5 one time. 3 goes into 21 7 times. I have a 17. Now, if you look on your prime number chart, you'll see 17 is a prime number, right? So it's not one of these Legos we've been working with. I just use kind of some of the common ones that'll show up. But with bigger numbers, we could get any prime number that there is. All right, so 17 is a prime number. So if I'm going to write this as a product of primes, I'll say there are 1, 2, 3 2's. So that's 2 to the third power, 1, 3, and 1, 17. So 2 to the third times 3 times 17 is the prime factorization of this number. We would need just a different color Lego for 17 if we wanted to represent it. All right, that's all I got for you. Good luck.